All right, Ian Swett from Google, who's going to talk about QUIC.
All right. So today I'm going to talk about the migration from gQUIC or Google QUIC to IETF QUIC, and then a little bit about what's next after that, but mostly kind of focus on that transition, because it turns out, technically speaking, it's a pretty huge one. And I put my email on this the slides specifically because if you have follow-up questions afterwards, feel free to contact me. Oh. Are they going? I must have the wrong button. Oh, it needs to use the, okay. Sorry, wrong UI. So I'm going to do an overview of what exactly QUIC is, kind of give you a little bit of background, compare IETF QUIC to Google QUIC, and then talk about the gQUIC to IETF QUIC migration, which is ongoing right now at Chrome and Google. So these are all metrics from the SIGCOMM paper in 2017. So QUIC is a protocol for HTTPS transport, at least initially. At the IETF, it's being more broadly defined, but initially it was for HTTPS transport. It was deployed to Google starting in 2014, quite a while ago now. It's deployed between all Google services and Chrome, as well as some mobile apps on both Android and iOS. So the most relevant number here for this crowd is the improved video rebuffers. So an improved video rebuffers between 15 and 18%, depending on its desktop or mobile, and certain environments like India benefited like a lot more. So places where the network was poor, in general, QUIC did substantially better. At the time, it was about 35% of Google's egress traffic, which is around 7% of the internet. I think a lot of you, if you run networks, probably have seen QUIC on your network, so it's definitely nothing new, and it's been there for a while. And then in October 2016, the IETF working group was formed, and that was kind of the beginning of the IETF process. So by IETF standards, QUIC is going quickly. It's like, only like 2 years in. It's an enormous project. One of the drafts is over 100 pages long, so it's a huge amount of technical documentation to get right, but hopefully it's getting pretty close to the end. So some key features. It's always encrypted end-to-end. I noticed the website for Mile High Video was an HTTP page, so presumably that was not delivered via QUIC. It's multi-streaming, so you can have multiple, in the case of HTTPS, multiple HTTPS requests outstanding at once, and they don't have head-of-line blocking between one another. So loss of a packet on one stream does not affect the delivery of data on another stream, which is one of the reasons why it can provide better video streaming is, one chunk in a dash request wouldn't block another chunk if there was packet loss. Has what's called zero RTT connection establishment. So the moral of the story is it saves somewhere between 2 and 3 round trips over a standard TLS or TCP connection. Better loss recovery, just because it's kind of designed from the ground up, and it has a slightly different design than the TCP sequence number design. You can mix reliable and unreliable transport. So for example, you could have a reliable file transfer that coexisted with a RTP data on the same connection. And it has better privacy and also has connection migration, certainly of interest. So what is gQUIC? What is IETF QUIC? What is HTTP3? These are common questions, and it's gotten a little muddled and a little bit confusing. And part of the problem is that when we first deployed QUIC at Google, it was only for HTTPS traffic, so it referred both to the HTTP aspect of it and to the transport aspect of it. So, but the moral of the story is that gQUIC generally refers to the thing that's actually deployed today. So it's deployed on top of UDP, uses QUIC crypto, has an HTTP mapping kind of all baked into it. You can think of it as kind of one monolithic chunk of code conceptually that's really designed for like excellent HTTP video delivery as well as other application delivery. IETF QUIC is, of course, the thing that the IETF is standardizing. It is just the transport. So it just gives you a multi-streaming API. You can open connections, you can close connections, you can send data, receive data, all of that stuff. And it uses the TLS 1.3 handshake, which is a newer version of TLS that was developed since QUIC was originally developed. And HTTP3 is the name for the HTTP mapping that lives natively on top of IETF QUIC. So HTTP3 is a mapping that will not be backported to TCP. At least that's the decision of the HTTP working group from around last year. So it's an entirely new mapping of HTTP that only works basically on top of QUIC, or if another transport came along that was similar, then it would work on top of that. Here's a nice visual diagram of this. So as you can see on the left, you have HTTP2, that's nicely layered on TLS, on TCP, on IP. And you can see for both gQUIC and IETF QUIC, the crypto layers are actually more embedded inside the transport. And it's almost like the transport's wrapping around the crypto layer. That is an intentional kind of visual distinction. It's not like a strict layering diagram, kind of like it is with standard TLS. So what's changed? The short answer is everything. So every single bit on the wire changed, which is why, from a deployment perspective, it's a little bit of a challenge. So some key changes are connection IDs went from 8 bytes to symmetric to variable length and asymmetric. The packet number used to be visible on the wire. Now it's encrypted. Used to we had bidirectional streams, which are basically request, response. Now there's bidirectional and unidirectional. The crypto handshake changed from crypto to TLS 1.3. We have a whole new header compression format that's designed to be optimized for minimizing head-of-line blocking. There are a ton of other changes that are small, but the moral of the story is kind of everything changed, but at a really high level, the goals are the same. Fast connection establishment, no head-of-line blocking, and to be a really, really excellent transport for HTTPS traffic. So this is a little bit of a segue, but this is a really common question, and I suspect a lot of people in this room have had this question before, which is, how do I get SNI out of QUIC, gQUIC in particular? So the short answer I'm going to give you for today is, if you haven't already done it, don't do it now. It's going to cause you a lot of pain and suffering because things are rapidly changing towards IETF QUIC, and we are moving to IETF QUIC as quickly as possible. And by the time you deployed something that got SNI out of gQUIC, I fear that we would now be on something that looked a lot more like IETF QUIC. So how do you get it from IETF QUIC? So I've written down kind of an overview right here. It's on my list to write up a very detailed synopsis in an IETF document so it can be used for future reference. But the SNI is only going to be in the initial long header packet from client to server. You have to decrypt those packets using AES-GCM 128. One note about this decryption is that the decryption is specific to the connection and the version of the connection. So you need to know there's a version specific aspect to the crypto. And so when a new version comes along, the crypto is going to slightly change. Not the type of crypto, but the crypto key generation. So the data is going to be inside a crypto frame, and inside that is just going to be TLS 1.3. So at that point, hopefully you can apply an existing TLS 1.3 SNI extraction library, and then you're done. Now, you don't actually have to write this code yourself for the most part. If you really wanted to, you could use an existing open source implementation of IETF QUIC. There are now over 10 written in various languages, and that would allow you to basically unpack the entire client hello and pop out crypto data for you. So, however, because this whole process is somewhat complex, as I just outlined, and is definitely subject to change when versions change, I would definitely suggest using destination IPs whenever possible, because it's likely to be much more stable, much more reliable, and especially for the short term, as we change from gQUIC to IETF QUIC, much less prone to accidental breakage. All right, let's talk about some of the issues we've hit in the migration so far. Recently, we went to gQUIC version 46, which is IETF invariance. So I'll step back one step. early on, we weren't really sure what aspects of the protocol we could version and we couldn't version in QUIC. And so we came up with this concept of invariance. So invariants are supposed to be things that never change between versions. So like, you can version negotiate in theory between version 1 and version 1000 because they share enough common components that you can kind of do that. Now, before we finalized the invariants, we changed them already. So they are technically the variants, not the invariants. But I don't think they will change again after QUIC v1, just kind of a side note. But v46 was designed with the old invariants in mind. And it was designed so like once we got on that, we can version negotiate, update all the way to IETF QUIC v1, v2, and so on and so forth. So the goal here was just to make the wire format look as much as possible like IETF QUIC in the hopes that from then on we would have fewer deployment issues. So yeah, the rest of this section is all about kind of that transition and the challenges it entailed. There's also a detailed doc on what exactly the bits on the wire look like in the header that's linked to, from the slides. So first I want to talk about QUIC identification. So this is fairly commonly deployed. I don't know if it's deployed in many of your networks, but certainly at enterprises they commonly do traffic classification, and so they can tell you how much of their traffic is this version of TLS, and how much is QUIC, and how much is RTP, and all these various other protocols. And also sometimes they'll decide, oh, I'm going to block this, not block that. You apply various policies based on that. So we've had a few problems with QUIC identification, particularly the blocking aspect. And one example of this is when we started deploying v46 at scale, we saw a huge increase in post-handshake connections being black holed. So that means the crypto handshake completes, we have keys, we think everything's hunky-dory, and then suddenly the network just goes silent. So this is very user visible. Users really, really do not like it. And it takes at least 30 seconds for Chrome to realize, like, hey, I'm just going to kill this connection and give up and move along. And in the meantime, the person's like hitting reload and getting understandably fairly upset. So we try to track this very closely, and we're pretty sensitive to regressions in this metric. Suddenly, on April 13th, it got better. April 13th is a Friday. We do not do rollouts on Fridays. We definitely don't do global rollouts on Fridays. It's not Chrome as well, because Chrome just didn't happen to have an update that day. But it went down pretty dramatically, pretty much overnight. It's not quite the same. It actually turns out it does taper down and actually gets all the way there, but that's a longer tail. But the question is, like, what happened? Like, it's not us, so what did happen? So let me back up a little bit and talk about like what this black holing metric really is. So QUIC, like TCP, has a concept of a retransmission timeout, which is like an exponential back off, and it just sends packets slower and slower until eventually you close the connection. In our case, after 5 consecutive RTOs of getting nothing back, we close the connection. So this is our kind of metric, our canary in the coal mine for saying, like, okay, whenever this happens, we think the connection is black holed post-handshake. Definitely a heuristic, but as we'll see here, it's a very, very good metric for post-handshake black holing. But the first question we had is, when is this happening? Because we don't know if it's happening 1,000 packets into the connection, like if they've been watching YouTube for 5 minutes, and so like someone's like, oh, you're watching too much YouTube, and they're just going to shut them down, or if like, it's a few packets into the connection. So we added some histograms, what they're called, and we found, wow, it's basically at 2, 3, or 4 packets. So it turns out that's the number of packets you need to complete a QUIC handshake. It's almost never more than 4. And so this is pretty strong indication that basically the handshake's completing and then you're just getting nothing afterwards. And as you can see, the rest of the distribution looks quite clean. So, this is great to know, but we still don't have a fix for it. However, we reached out to some people who previously had done some QUIC identification and found out that they had recently updated their identification, and when they updated it, it dropped. And so apparently that was the fix, and that was what got rolled out that Friday. More recently, we found out that they didn't actually update everyone globally at once. They actually have a long tail of people that they only update quarterly. So then we spent a bunch of time trying to debug some other user that also had the same issue, but it turned out really they just hadn't updated their software. But you know, it was a lot of debugging and kind of a quirky answer. But the nice thing is we now have metrics we can authoritatively say, like, this is what black holing looks like, and we can quantify like when in a connection it's happening. And so it helps us like really debug these like quirky like edge case issues that can happen inside a network. So here's some like requests on, if you're gonna block QUIC, here's how I would like you to do it. If at all possible, can you ensure that all packets in at least one direction or the other are completely blocked? So that ensures that the handshake can't succeed and the user doesn't, you know, get stuck there waiting for the spinner and, you know, waiting for the loading bar to load when it's never really gonna happen. I'd like to point out this is true for pretty much anything, like DTLS would have this property, like anything that is a connection-oriented protocol does not really appreciate having like a few packets go through and then all the packets get dropped. So HTTP3 clients do have a fallback, and Chrome does have a fallback to TCP, and it will eventually like start using TCP in these situations. But the learning scenario takes a while and is fairly like frustrating. All right, so here's another one where we ran across in the V46 rollout. Suddenly one day, QUIC usage among Windows users only dropped a fair bit. So we were very confused by this. Originally, we thought it was this other network issue change because they were around the same time, but then we like dug more and more, and they were completely unrelated. It was eventually traced to a single antivirus company that was not blocking V46, but was blocking V43, which is like the default at the time. So we, you know, hopefully said, well, let's enable V46 because obviously they like that better. And at the time we said, maybe they read the IETF drafts and said, I will accept QUIC versions that conform the IETF invariance. That would have been very nice of them, you know, like forward thinking, like I'm gonna encourage adoption. That wasn't what was happening. They were just trying to block QUIC and they haven't read the drafts. And so as soon as we enabled V46, they blocked that too. But, you know, at least now we know. So the final change that you know, kind of caused some breakage in a few networks being encountered is that the SNI changed in location. I think probably only by a byte in most circumstances. And so I'm a little surprised this actually caused breakage, but some middle boxes have started doing SNI extraction for gQUIC. Most of them haven't really told us yet. And so if you haven't told us and you think our network people don't know and you are doing it and you don't want to get broken, please, you know, feel free to drop me an email and I will try to make sure you're on whatever list we have of notifications. But, you know, breakage is a real risk because we don't even know who we're breaking. And unfortunately, in order to make the progress towards IETF QUIC and end up so we're all finally on the standard, and so that standard is working for everyone, whether it's Google or Netflix or, you know, Akamai and everyone else, we need to make some more changes, and like it's going to be a bumpy road to get there. And so there's probably going to be a few more changes before IETF QUIC that actually break this yet again, unfortunately. So what's next? We're getting a lot closer to IETF QUIC. We're not quite there. Some things are going to break. In terms of video delivery, one of the really exciting things that's on the horizon for IETF v2 is it's been identified that most people think that WebRTC actually potentially could be the next big application. And so, you know, I know there's a lot of people who use WebRTC in this room. And, you know, if you want to be involved in that process, I would encourage you, and you're willing to deal with the IETF, I'd encourage you to, you know, follow along whenever that process starts and, you know, add your 2 cents. So at the bottom, I have some links for mostly the IETF working group documents. Of particular note is the applicability and manageability documents, which are kind of more on the usage of QUIC rather than the core transport design, but there's also the core transport design and the Chromium code as well. So Questions?
Hi. So you didn't say it explicitly. Can you please tell us if YouTube or any other Google will end support for Google Quick and move to IETF? And the second question is, what's the motivation to do a variable length header in networking?
Sorry, what was the second question?
What's the motivation to do a variable length header? You modify the packet sequence number to a variable length.
Oh, the variable length. Oh, the variable length connection ID. Yes. So I should have added the subtext of this talk is yes. Google is very much committed to moving to IETF QUIC as soon as it is done. I almost added a slide that said that like when is Google going to be on IETF QUIC? When it's done. It's not done yet. It's still a draft version. That being said, we plan to deploy a draft version before like final adoption to make sure we get some deployment experience. And we are working on that as hard as possible. We've already achieved interop with about 10 other, or maybe 6 other HTTP3 implementations. So code-wise, we're a long ways in, and we're getting pretty close. But I can't give an exact date on like when Chrome or when Google will actually enable a draft version yet. But a lot of people have that question. In terms of the variable length connection ID, originally it was 8 bytes for routing. The reason it changed to variable length is that some people wanted to do crypto. And if you want to do crypto, the most convenient crypto primitives are actually 16 bytes. And so some people wanted to encode like the server ID and some various other parameters actually in the connection ID itself and use that as like a global routing identifier. So for example, no matter what middle box, like on your large network it hit, the middle box could decrypt the connection ID, look up what server to send it to, and like send it to it. That's as an example. So that was a use case. And I think Akamai, for example, was one of the people who were interested in that type of functionality. Yeah.
I have to apologize. I haven't been following the IETF work. Where is non-reliable in the IETF spec? It never really made it into gQUIC in the client.
So currently, the only thing that is unreliable in the IETF spec is it's permissible to cancel streams. So cancel, for example, a request, and then basically like not retransmit the data. This seems like a pretty crude primitive, but it actually turns out we actually did an implementation of WebRTC over this primitive, and it works out quite well. So you can add a TTL to a stream. If the video or audio doesn't get delivered in 100 milliseconds or whatever the jitter buffer time is, you just cancel it and you don't retransmit it. So there's definitely like more work than that, I think, in V2, but that's kind of the current primitives that are available.
Okay. Anybody else? All right. So, by the way, there's a little irony in this, but we'd have to leave it to you to be the quickest presenter so far. I'm here till Friday, that's right. All right, so we give it a round of applause.